Well, thank you very much. Thank you. First of all, I would like to thank the MAA and the organizers of this amazing conference for inviting me here to talk to you today. And thank you all very much for coming and giving me the opportunity to reach a literally wide audience. As I am a woman and a mathematician, I am often asked about the issues of women in mathematics, and I'm sure if you are a woman here, you have also been asked this question. And I used to be very reticent to talk about it because I didn't want to draw attention to it. But now I've become the opposite of reticent, which I suppose is keen, and I'm now very keen to talk about it because I think it's so important and urgent, and because I don't think that we've made enough progress in recent times, although we have made some progress. And I've had, as Emily described, a perhaps unusual career path during which I've had many opportunities to learn different things about why people get put off math at which points and how they can be attracted to math again. And I want to share these things that I have learnt as widely as possible. So this is not formal research into pedagogy, but it is from a lifetime of, well, not as many years as some of the amazing long-standing members we celebrated last night, but from 20-odd years of teaching mathematics at all sorts of different levels. And what I've learned about who likes it, who doesn't like it, and what those reasons are. So I'm going to talk about there are kind of two parts to this talk. The first is things I've learned, and the second part is what we perhaps could do about it. I decided I should change that from should, because should sounds very prescriptive, and I don't like telling people what to do. But this is something that we could possibly consider doing about it. So in the first part, I'll tell you about my background teaching different types of undergraduate students. First, math majors at some very distinguished universities, and now art students at art school in Chicago. I will discuss what I believe is a more productive way of thinking about these issues by talking about character rather than gender. So sometimes gender is important because of bias and prejudice that people have. But when it comes to actual mathematical ability, I think we should stop talking about gender and think about character types instead. And I am going to propose some new terminology to help us with this. I think as mathematicians, we know how important terminology is at the beginning to get our heads in the right places. And once we have good words for things, we can study them more easily. So then I will talk about how I have used this approach to transform how I teach mathematics in a more inclusive way, and specifically to attract people who have previously been put off math. Then, in part B, I will talk about how category theory fits in with this, and how I strongly believe that category theory can be taught as a very inclusive type of mathematics, even to high school students. I've just finished my first iteration of a high school summer camp that I did in Chicago last week, and I did category theory with them. And it was a very short camp, and they were eager for more. I will talk about the sense in which category theory does various things. One is it studies relationships. It studies different and more nuanced notions of sameness, which I think are relevant to how we think about the world. And finally, how we should consider everything to be in context. And all the way through, I will give examples that partly come from my next book, and that are inspired by my teaching of art students and the kinds of things that motivate them. So first of all, my background. As Emily said, I previously taught math majors at very standard research universities, the University of Cambridge, the University of Chicago, and the University of Sheffield. They were all people who had done very well in high school math. They had typically been the best in their school at math, and they arrived at university convinced that they were great at math. And I'm sure you've met students like this. And they are destined for careers in math or science or engineering or finance or accountancy, sometimes law and sometimes teaching math. And they were very heavily male-dominated. So the last class I taught at the University of Chicago was less than 30% female. I now teach at the School of the Art Institute of Chicago, which is a very high-level art school. It is a liberal arts school, so everyone has to do something, but everyone is doing a fine art degree. They're either doing painting or drawing or sculpture or fashion, a few architects. And most of them did not do well in high school math. Many of them have very bad memories of it. Some of them did well, but then gave up because they wanted to be an artist. They're going into careers in art, design, photography, sometimes art education. They're definitely not going to go into mathematical careers. They think they're terrible at math. And, interestingly, it is very female-dominated. So typically my classes are 90% female. Despite the fact that art school is female-dominated, it's about 60% women at the School of the Art Institute. For some reason, women are overrepresented in my classes. So I have taken the opportunity to study what put those art students off math. They are very serious students, and they are very self-aware, and they love reflecting on their experiences in education. So it's a great opportunity for me to really get to understand all the different ways in which they have been put off. And so memorization comes up a lot. I asked them to write me a kind of autobiographical essay at the beginning of the semester about their past math life and what they feel about math. And the thing that always comes up is they hate math because it involved memorizing things. They hate math because of times tables. They hate math because of formulae that they don't know where they came from. They hate math because they got things wrong. And they prefer subjects where there is no such thing as right and wrong, where you create things. They have a false dichotomy between art and math. So some of them say that they quite liked math, but they knew they wanted to be an artist. And it seemed like you're not allowed to like both of those things at the same time. And you're certainly not allowed to study them both at the same time. And finally, they hate math because it has no creativity. So I'm sure we can all recognize these things the other way around, and it makes me sad because these are almost the exact reasons that I love math, just the wrong way around. So the reason I loved math was because I never had to memorize anything. Because as long as you understand it, then you don't have to memorize anything. Unlike physics, where I felt like I had to memorize tons of stuff. So they hate math because of times tables. I never learnt my times tables. I know my times tables, but I did not learn my times tables. I did not have to memorize any formulae in math. I only had to memorize formulae in physics. And the thing about getting things wrong is, well, it's true I didn't get that many things wrong when I was little, but then once you get to a research level, it's not really about right and wrong anymore. And every time I say this on Twitter, people get really mad at me, usually white men. But that people don't understand that math is more about understanding things and figuring out how things work and justifying things and exploring, rather than about right and wrong. And especially my field of research, I feel, is not just about getting the right answer, but about illuminating so that we can reach a better understanding. Of course, there is not a dichotomy between art and math, and of course math has creativity. We know that, but for some reason, other people don't know that. And of course, it's because many people's experience of math classes have a total lack of creativity. But it's sad that they think that is math. So I had dance lessons as part of dreaded PE when I was 11. And the dance classes consisted of a teacher putting on some dreadful electronic music and teaching us to memorize a series of steps that we then had to perform all at the same time to this awful music. It completely lacked any creativity. But I managed to grow up still believing that dancing involves creativity despite this class. So somehow math is not getting that message across. So I propose that there are some character traits that we should think about in both humans and in mathematics, in fact. And I propose some different terminology because I think that the terminology masculine and feminine is extremely obstructive, and it's prescriptive, and it causes people to feel like something is wrong if they are doing something else. And my experience of being a mathematician in a very male-dominated world was that when I was young, I wanted to hide all signs of my femininity in order not to draw attention to it. And then, as I became more secure in my position, I felt okay showing some signs of femininity, but mostly outside work. And then I felt like I had a weird dichotomy between my outside work life and my work life, and then I decided to try and blend them together. I realized that none of this makes any sense, because everything I do is feminine because I'm female. So I've decided we need new terminology, because both men and women are oppressed by the kind of expectations that society puts on us, even if we fight against it, there's some notion of masculinity that men are supposed to live up to, and if they don't, then there's something wrong with them. And there's some notion of femininity that women are supposed to be, and if they do things that are considered more male, then they get criticized for being strident or angry or something. So I propose to replace the word masculine with the word ingressive, and the word feminine with the word congressive, and then to forget that we ever had those gendered words in the first place, and think about what these terms might mean. So ingressive is supposed to indicate going into things, and congressive is to indicate bringing things together. And I would like to stress that this is not a straightforward dichotomy. It doesn't mean that everyone is one thing or the other. You can be different things to different extents at different times, and importantly, these are not fixed character traits. They are things that you can learn. So I know that when I was trying to be a successful research mathematician and climb that career ladder, I was trying to emulate ingressive behavior as much as I could because it seemed like that was what I needed to do to be successful. And I hated myself for it, and that's one of the reasons I quit. And now I'm pursuing life in a much more congressive way, and I feel much better about it, and I feel like I'm helping more people. So here are some ways I think of as characterizing the difference between ingressive and congressive character traits. So one is that ingressive people really like winning, whereas congressive people hate losing. And I realize those are very slightly different things. And so I am determined to win, but only because I hate losing so much. Whereas if a situation has no concept of winning and losing, then I really don't care. Ingressive people really like being right, and a congressive trait is hating being wrong. And I think that this helps me understand why some students are really keen to call out answers in class and why other students will not speak in class. And I was the latter kind. I did not speak in class ever. And I'm still very reluctant to speak even in research seminars. So ingressive is calling out answers. Congressive is reluctant to speak in class. Ingressive people like solving problems. And congressive people like discovering and understanding things. So there's enjoying being right and wrong as opposed to enjoying creating and building things. Ingressive might be associated with being competitive, where congressive is more about collaboration. Ingressive people, I would say, overestimate their own abilities. And congressive people underestimate their own abilities. And we can say things like, in my experience, at the beginning of the year, there are always some students who think they're fantastic when they're not, and they're usually men, but not always. And every time you have to say usually, but not always, you get yourself kind of tied up in knots. Whereas then there are a whole load of students who cry in my office because they think they're doing terribly, but actually they're doing all right. And they're typically female, but I would rather talk about this as ingressive and congressive character traits. And I would always rather work with someone who underestimates their own abilities. So I suspect that ingressive people like high school math more than congressive people, because I think that high school math tends to be quite ingressive. It's about getting the right answer and doing it fast. And I suggest that it's a bit like that thing about being from Mars and Venus, which I actually found that book quite illuminating, but you have to spend the whole thing going, well, not all men and not all women. And changing this terminology frees us from that, and we can just think about character traits instead. So here is how I have turned from an ingressive math teacher into a congressive one. When I started, the only place I'd ever had math lectures was the University of Cambridge, and I gave my first lecture course at the University of Cambridge, so I did it the way everyone else did, and gradually realized that this was not the way I wanted to do it, and I didn't think it was productive. You know, the way where you stand at the chalkboard, write as fast as possible, speak at the same time, and everyone frantically takes down notes and doesn't absorb anything. So I think that ingressive math is all about just written symbols, whereas congressive math involves a lot of visual and physical aids. Ingressive math focuses on outcomes, whereas we should focus on processes. Instead of focusing on facts, we could focus on discovery and investigation. Instead of rules, we could focus on choices and opinions, because those rules are there for a reason. And if the rules are imposed without explanation, then it's like being in a dictatorship where there are just arbitrary rules imposed and you don't know what's going on. So I always tell my students they can make up any rules they want as long as they follow them. And if their rules cause a contradiction, then their world implodes. But that's all right. It's an abstract world. You just start again with a different one. So instead of formulae that produce answers, we have reasons. And sometimes those formulae have really interesting reasons behind them. Sometimes they don't. So ingressive is about solving problems, but I think congressive math is more about building structures. And this speaks to Tim Gowers' very interesting essay about the twin cultures of mathematics, problem solving and theory building. And problem solving is more glamorous and achieves more fame and is more likely to get you a Fields Medal. Ingressive is about calculating answers, and congressive is about uncovering relationships between things. So this is a picture of one of my favorite relationships between a slinky and a bagel. And everyone says, how did you get that in there? Well, I cut the bagel open and inserted it in, and then hid the cut. So the way I teach math, I used to do traditional lecturing, and now I do more project-based learning. So possibly not what's technically known as project-based learning when you have one project for a whole year or something, but in every class I do a small project that involves exploration and discovery. So instead of having a right answer and a wrong answer, it's a low floor and a high ceiling project, which means everyone can get into it, but then there's basically no limit to what you can discover, and anything you do will consist of a discovery. There is nothing right and nothing wrong about it. Instead of competitions, there are many math competitions which are for outreach in mathematics, and those appeal to a certain type of people, ingressive people. I hate competitions, and I'm very glad I was never put in for a math competition when I was a teenager, because if I had been, I'd have thought, oh, I'm terrible at this, I shouldn't be a mathematician. Fortunately, I had never heard of math competitions until I went to university, and everyone said, did you do the Olympiad? And I went, what's that? So I really like Julia Robinson math festivals, and I've been involved with a couple in Chicago. And if you don't know what they are, you have various tables with activities on, and everyone can just spend as much time at each activity as they feel like. Instead of math games, there are many math games that make math fun, but only if you like games. I don't like games. I don't like any games. However, I love crafts. So math crafts appeal to, I think, congressive people. And sometimes people say to me, oh, I'm so glad you said that. I thought I was bad at math because I hate all those math games. And so we're putting people off for the wrong reasons. So instead of puzzle books, which I find quite tiresome, I love books like Christopher Danielson's Which One Doesn't Belong, where every page has a set of 4 things, and all of them cannot belong. It just depends what you decide to choose as your criteria. And so it focuses on the process and the justification instead of the outcome. And I love this book, and I urge you to check it out. So how is category theory congressive? So I think that the math that we tend to present in high school and in outreach and even as undergraduates is very ingressive. And I personally did not feel mathematically at home until I met category theory. And I think it's, in retrospect, I think it's because the undergraduate system was too ingressive for me. I was able to make myself ingressive enough to be successful enough at it to get by, but I didn't enjoy it, really. And in retrospect, I don't think it was productive for me. So category theory is, I think, a bit different from the kinds of math that we tend to push, for example, calculus, calculus, and more calculus, or solving more and more problems. So I think category theory is congressive because it's about understanding structure rather than problems and answers. It focuses on relationships between things rather than inherent characteristics. It gives us different ways in which things can be the same or not. And so it's not about right and wrong answers. It's in what sense is this thing true over here, and in what sense might it not be true over there? And I think this is a much more congressive way to approach arguments in the world as well, as I'll show, that it's not that one person's right and that someone else is wrong. It's that we should find the sense in which this person is right and the sense in which this other person is right, and then we can reach more unity. So it's also about making connections between different ideas and different parts of math. And it grew up from wanting to make connections between topology and algebra and various other things. And now we've discovered we can make connections between all sorts of places. And that is fundamentally what I call congressive, because it is bringing things together. So I will now show you some category theory. If you haven't seen category theory, this will go from the start. If you have, this might be some applications of category theory that surprise you, unless you've seen me talk about this on a video already. So as Emily said, I like to say that category theory is the mathematics of mathematics. And in order to explain that, I first have to say what I think mathematics is. And it's surprising how baffled people look when I say, what do you think mathematics is? I actually start every single course I ever give by asking all my students what they're doing here. So I say, what are you doing in education? What are you doing at this school? What are you doing in this class? And now, what do you think mathematics is? And particularly math majors are very baffled by this question because they've never wondered what mathematics is. So I say that mathematics is the study of how things work. But it's not the study of how any old things work, it's the study of how logical things work. And it's not any old study of how logical things work, it's the logical study of how logical things work. And of course, nothing actually does behave logically. I don't behave logically. Even Emily doesn't always behave logically. The computer doesn't behave logically. And so that's why we have to become abstract, because we have to get rid of the pesky details that stop things from working logically. And we go abstract, that takes us to the abstract world. So category theory can be thought of as being very abstract. Some people say it's too abstract. Some people call it abstract nonsense. Whereas I say that the abstraction has a purpose, and the purpose is to be able to make connections between more things. And when you become more abstract, you get to encompass more examples. And I'll show that I encompass some quite surprising examples from real life into my study of category theory. So this means that category theory is the logical study of how logical things work. But I hope to show you that this doesn't mean that it is too abstract. So here is one of my favorite examples of something categorical. I consider it to be categorical. It is the standard map of the London Underground. Now, this map is not geographically accurate, but it just shows the connections between things. And so when you're actually trying to take the tube, it doesn't really matter exactly where the tunnel is going when you're in the train. What you want to know is how the train lines all connect up with each other. And it's those relationships that we're interested in for this particular use. And this is what category theory does. It says, which relationships are we interested in for this particular context? Let's focus on those for now. Maybe in another context, we'll focus on some different relationships. So here's the geographically accurate map of the tube map. It's completely impossible to use if you're trying to get anywhere, but it's quite interesting to look at. So it's not totally useless. It's just useful for something different. So category theory focuses on relationships between things. And these relationships are often drawn as arrows, but they can be actual relationships like is the mother of. And then we could have B is the mother of C. And these types of relationships compose. Now, being the mother of is not transitive, because if A is the mother of B and B is the mother of C, A is not the mother of C. But A is the grandmother of C. And in order to say that, we need to allow for slightly different types of relationships inside one context. So we could do this again with A is the sister of B and B is the mother of C, and then we get that A is the aunt of C. And this is the notion of composing relationships. So it's a generalization of transitivity. And composition in a category means that we can omit any arrows that we can deduce. So we can omit these arrows because we can deduce them. So what is a category? Well, it consists of some objects that we're studying and some relationships between them, together with composition, like I just showed, identities, which says everything is related to itself in a trivial way, and associativity and unit laws. So associativity says if A is the mother of B and B is the mother of C and C is the mother of D, then we could do two things. We could say this, or we could say that. So associativity says that the grandmother of my mother is the mother of my grandmother. We look at a lot of commutative squares inside category theory, which is when going two ways around a square gives you the same answer. And one of my favorite examples from when I was little, I didn't realize I was doing category theory, but I was really. And this is true of people don't realize they're doing math when they are really, and many mathematicians don't realize they're doing category theory when they are really. So we had some family friends who were two brothers who happened to be married to two sisters. And I found this very intriguing. So A is the brother of B and C is the sister of D, and they're married like this. And so this is a commutative square, because if you go around one way, you get your husband's brother, who is your brother-in-law in English, and the other way around, you get your sister's husband, who is also your brother-in-law in English, but they are not typically the same person. Whereas in this situation, they turned out to be the same person, which means going both ways around this was the same. Now, I encountered another commutative square recently that I actually had to draw the square before I could understand the situation. I went to a party, and everyone was playing Super Smash Brothers, which I had never heard of before, being someone who doesn't like games. And however, there was someone called Alex who wasn't even at this party, but Alex went to high school with Spencer and went to university with Nate. And Spencer went to university with Greg and told Greg he had this friend from high school called Alex who's really good at Super Smash Brothers. Meanwhile, Greg went home and told his high school friend Nate And Nate said that he met someone at university who's really good at Super Smash Brothers, and they turned out to be the same person. And this was explained to me about 8 times, and finally I drew a commutative diagram. And then I understood it. So commutative diagrams appear in all sorts of categories, and here is one of my favorite categories. And this is an exercise I do with students at all levels, from middle school all the way up to undergraduates and research mathematicians. So if we look at the factors of 30, and we just say what they are 1, 2, very good. Right, we're mathematicians, not calculators. And this is a bunch of numbers in a straight line. It's not very interesting. And we live in a 3-dimensional world, so we write on 2-dimensional pieces of paper in 1-dimensional straight lines. So we stuff our thoughts into 1 dimension. Sometimes they want to be in higher dimensions. They have some natural geometry in higher dimension. So now we can construct a category here where the arrows are going to indicate when something is a factor of something else. So 30 goes here. Now, we have arrows to its factors, 6, 10, and 15, and we don't have to draw arrows if we can deduce them from a composite. So 5 goes into 10 and 15, 2 goes into 6 and 10, 3 goes into 6 and 15, and 1 goes into 2, 3, and 5. So now we see it's the vertices of a cube, which I think is a bit more interesting than a bunch of numbers in a straight line. And this, you can take this project in all sorts of directions. You can just let the students go and investigate what shapes you get from other numbers and which numbers will give you the same shape. So you can notice that this is because it's got 3 distinct prime factors. And so, in fact, if we write down the factors at each vertex, we get this, and then we see it's really just subsets of prime factors. And so if we go one step more abstract, we might as well just call them A, B, and C. And now we can immediately see some other numbers that will do that. So any number that has 3 distinct prime factors will give the same structure of arrows, which is the same category, basically. So for example, the factors of 42, which is also a product of 3 distinct prime factors, here they are. Now we can build the same diagram, starting with the prime factors at the bottom, then the product of 2 prime factors and the product of 3 prime factors at the top. If we restate this in terms of the prime factors, the middle diagram is the same as the middle diagram on the previous slide, but with every 5 replaced by 7. And then the abstract version is the same. So you see that once you reach a good level of abstraction, everything becomes the same. Now, there's something I'd like to stress about this diagram, which is that 6 is less than 7. That doesn't sound very profound, but 6 is higher up in this hierarchy than 7, which is kind of interesting because it means that we've got 2 different orderings on the numbers and they don't match up. So there's not an order-preserving map between them. And this is very similar to what happens in life when you have 2 different hierarchies on the same set of people and they don't match up. So perhaps seniority in a job environment does not match up with age, and then that can cause antagonism between those 2 different hierarchies. So the point of this abstraction, now people say, oh, I was fine with math until the numbers turned into letters. But the point of turning into letters is that the letters can now be anything. So for example, they could be 3 types of privilege: rich, white, and male. And then at the next level down, we'll have people with 2 types of privilege: rich, white, rich male, and white male. And then at the next level down, people with only 1 type: rich, white, or male, and then at the bottom, people with none of those types of privilege. So if I put back in the missing words, we have rich, white, non-male, rich, non-white male, non-rich, white male, rich, non-white, non-male, and so on. Now, rich is, of course, a moving target, and most people like to think that they're not rich and that the rich people are other people. I'd like to urge you to consider that everyone in this room is rich compared with many people in the country. So this diagram now tells us some important things about how privilege works. And some people mistakenly think that privilege means that all white people are better off than all black people. And this is not what privilege means. Privilege means that if you move directly down one of these arrows and lose one type of privilege while everything else stays the same, then we would expect you to be worse off in society. And so some people point at super rich black sports stars and say, look at them, they're really rich. That shows that there is no such thing as white privilege. That is not what white privilege means. So there's something else we can understand from this diagram, similar to the fact that 6 is less than 7. So if we look at the absolute amounts of privilege along the top row, right, in this partially ordered set, those 3 objects are not comparable. But we can think about how well off those people typically are in society. And we can maybe agree that rich, white, non-men for example, are probably better off than rich non-white men, who are in turn better off than non-rich white men. Because it turns out that money mitigates for many things in life. So the same is true of this level. So it's actually more skewed. And then if we compare the two levels, maybe we can agree that actually riches mitigate for so many things that, for example, rich black women are probably better off than poor white men who are maybe unemployed and homeless. So it's actually skewed like this. So it's a cuboid of privilege, not a cube. And this has helped me understand why some poor white men in society are so angry at the moment. Because they are considered to have many types of privilege, but they don't feel any manifestation of it, because they feel in absolute terms that they're worse off than many people considered to be less privileged than them. And I think it's more productive to understand the structural source of this anger, rather than simply to get angry with them in return. Thank you. So moving on to questions of sameness, which is one of the things that category theory really focuses on. So all equations are lies. I admit that's a bit clickbaity of me. But here's what I mean, right? 8 plus 1 equals 1 plus 8, but it doesn't really, right? One of them says take 8 things and add 1. If you ask a small child to do that, when they're still only counting on their fingers, they'll put 8 in their head and count on by 1, and they'll get 9. If you give them 1 plus 8, they'll put 1 in their head and try and count on by 8, and they'll probably get lost. So the 1 plus 8 is harder, and that's why this equation is useful, because it means that we can pick whichever one is easier, right? So the entire point of an equation is that something about those two sides is not the same, and that we can use the sense in which they are the same to pivot between the two things that aren't the same. So the same is true of 2 times 5 times 5 times 2. 2 times 5 is 2 bags of 5 cookies each. 5 times 2 is a waste of plastic. And here is associativity, which also says, well, I think one of these is much easier, because 5 plus 5 is easy. I can do that. 8 plus 5 is hard. That goes over 10. I have to think to do 8 plus 5. So the only equation that's really not a lie is x equals x. So I suppose what I really mean is all equations are lies or useless. I'm sure you, like me, have had trouble persuading your students not to write 1 equals 1 ever. And it will come up and they think it's useful, and it's not. It's really not useful to write 1 equals 1. So here is an example of where associativity is a bit more subtle than that. Here are 2 different ways of representing associativity in a way I like. Here, this one says add 4, which is Yate usually. And then you add 2, so this makes 10. And we usually write it like this because we've stuffed ourselves into a straight line. The other way around says add the 4 and the 2 first, and then the 4, which we write like that. So this is the associative law for addition. However, if we're studying objects that are more interesting than numbers, and there are many objects that I think are more interesting than numbers, for example, we could use egg yolks and sugar. We mix egg yolks and sugar together, we heat it up with some milk, we get custard. If we do it the other way around, we mix the sugar and the milk together first, and then we mix in the egg yolks. We do not get custard. However, when you're making cake, it doesn't matter so much. So the recipe I grew up with says cream the sugar and the butter together first, mix in the eggs, and then beat in the flour and bake it, and you get cake. However, it turns out, especially if you have an electric whisk, you can just kind of chuck everything in a bowl and go, wah. So it really depends what you mean by the same. And in higher dimensional category theory, we spend a lot of time deciding which things we want to count as the same and deciding what is a good context to consider them to be the same. And we do this in a basic category with the notion of invertibility. So if you add 4 to a number, you can definitely invert that by subtracting 4. That's invertible. Whereas if you square something, it's a bit more tricky. How do you get back again? It's not clear. So F and G in a category are called inverses if composing them that way around gets you back to the identity, and composing them this way around also gets you back to the identity. And then those two objects are called isomorphic. And the point is that the category treats them as the same because of the relationships they have with everything else in the category. So the category only sees the relationships that objects have with other objects. So if you have this situation of isomorphic objects, another object looking at A and B, well, whatever relationship it has with A can be turned into one with B via that arrow, And any relationship you have with B can be turned into one with A via that arrow. So X has exactly the same relationships with A as with B, and so it can't tell the difference between them. And things can be isomorphic in one category but not another. So one category will tell the difference between them and another category won't. And this is true in life as well. So sometimes things count as the same and sometimes they don't. Here's a picture of an egg that I froze and then I thawed. So if you've ever done this, it's quite odd. The yolk just kind of sits there. So here's a zoomed in. It's just sitting there. Now, you might think this means it's not the same, but actually I've spent quite a lot of my life just eating egg whites because I used to be quite fat and I lost weight and don't want to put it back on again. So I spend quite a lot of time separating eggs. And if you're going to throw out the egg yolk, it's way easier like this because you can just pick it up and throw it out. So actually, it doesn't matter to me that this counts as the same to me. So whole categories can be isomorphic to each other if they have the same arrow structure. For example, the power relationship that male people have over female people is isomorphic in a sense to the one that white people have over black people, which is also isomorphic to the one that rich people have over poor people. And however, the male people's power over female people is not isomorphic the other way up. So if you try and map the male people to the female people at the bottom here, those arrows will be pointing the wrong way. And that means it is not an isomorphism of categories. And this is a sense in which when men are sexist towards women, it is different from when women are sexist towards men because of the underlying power difference and the fact that these categories are not isomorphic the other way up. There is a sense in which it is the same because it's people being terrible to other people. But there is also a sense in which it is different, and that is this. So equality should be like equality, sameness in a category, I think. It doesn't mean that men and women are the same. It means that we should treat them the same when it's not relevant that they're men and women. It is relevant if you're having a baby. Apart from that, it's really not very relevant. So finally, I'd like to talk about how category theory characterizes things by the role they play inside that context. For example, in these three places, the male people, the white people, and the rich people are playing an analogous role. And in these three contexts, 30, 42, and rich white men are playing an analogous role. And once we've seen the category structure of something, we're not thinking about intrinsic characteristics anymore, we're thinking about relationship structures. So we can look for things that play analogous roles between different places much more easily. And one way we often do this is using a universal property called an initial object, which is an object I such that for all objects x, there is a unique morphism from I to x. So it's initial because it's at the beginning of all the arrows. So for example, in these three categories, the male people, the white people, and the rich people are initial. In these categories, 30, 42, and rich white men are initial. So they have that universal property. Now, different people can be at the top in different contexts. So different objects will be initial in different contexts. Here is the original cube of privilege, although now we know it's a cuboid. That doesn't matter to the category structure. So rich white men occupied the initial position there, but if we restrict to this part of the diagram, which is the non-men, we see that rich white non-men are now the initial objects in this context. And in fact, we could restrict our entire attention to just women, and we could take rich, white, and cisgendered as our three types of privilege. So remember that cisgendered means that your gender identity does match the identity you were assigned at birth. So now we see that rich white women, rich white cis women, occupy the analogous position that rich white men do in wider society. And this has helped me understand why there is so much anger towards rich white women at the moment in the feminist movement, because they tend to see themselves as underprivileged relative to men, and they don't see how privileged they are relative to other women, and this causes antagonism. So I think that we could, I don't like to say should, but we can, and I certainly do, use abstract structures to help me understand things from different points of view. I can pivot between different contexts in which I occupy different positions in order to understand what it's like to be in different positions. We're all overprivileged relative to someone and underprivileged relative to someone else. So we could all do these pivots. And it is possibly a surprising fact that it is very abstract mathematics that has helped me to understand these social issues. And I know that I use these abstract tools all the time because my brain is so trained to do that. And I've realized that if I make those explicit, then I can help other people to do it as well. So in conclusion, I would like to see math taught more congressively, and I also would like us to teach more congressive math more congressively. And I think that category theory is an example of congressive math that works at many levels. It unifies the highest levels of research math, and it also helps us understand social interactions and political arguments. So on Saturday afternoon, we're having an invited paper session called Category Theory for All. Here are our 4 wonderful speakers, and I've asked them all to make it extremely accessible, and so I hope that if you're interested to find out some more, you will come along and hear some more about category theory. So I would like to finish with a quotation from a student of mine in their feedback, who after 1 semester of doing abstract mathematics and category theory at art school, wrote and said, "Now I find that math is not just a tool, and the real reason for learning math is to practice our thinking." Thank you very much.
Thank you so much. So firstly, I want to invite people to get up and leave. I know this is a busy day. People have other places to be, but we do have some time for question. Would you please use the microphones on one side or the other, just so everybody can hear your question as well?
Do we have no questions? Is everyone too congressive to ask a question?
Could you tell us specifically where to find your YouTube videos?
Oh, well, if you go to my webpage, which is eugeniacheng.com, there is a page of videos, and there are videos at various levels. So there's the original MathDoes channel, which is very low tech, but I'm quite fond of it. We just pointed a webcam at a chalkboard. And so that's for category theory, aimed at people who want to learn technical category theory. Then there's a series called the MathFest, which was aimed at high school students and beginning undergraduates to give a taste of what I think mathematics is really like. And then there's a summer math series, which is more for elementary school students, which is very high-tech, with a team who spent ages editing it. It's got tons of graphics and effects, and it's very complicated. And then there's a series called The Master Chef, which the University of Sheffield made with me, which is aimed at a general audience, and it's where I use food in all sorts of ways to explain various concepts of math and show that it's fun and messy and hilarious.
Thank you.
Thank you.
Hi.
Hi.
I'm wondering about the practice by which we can talk about social constructs to non-mathematicians. I mean, we might think of these terms in terms of category theory, and it's pleasurable to do so, but most people probably don't.
Could you say that again, because I missed the beginning?
Oh, I'm wondering about the, now I'm closer. I'm wondering about how we can talk about these social constructs to non-math folk, because we might think of them in terms of category theory.
This is how I talk about it to non-math folk. I don't give them the definition of a category necessarily, but I have also done that with non-math folk, and it has gone down very well. And so this is actually what my next book is about. So there are some copies, preview copies here, if you'd like them, where I explain how we can use these things to understand. So there are a lot of diagrams, and people, non-mathematicians, have told me they found the diagrams really illuminating, because it's, if you try to write, for example, if you try to write that cuboid of privilege as an essay with no diagrams, it would be extremely convoluted, whereas you could sum it up in this diagram, and that's one of the lessons of category theory, that sometimes diagrams can just show us all the interactions very quickly. You don't have to understand any category theory to appreciate the interactions in that diagram, I think. And this has been shown to be true. I give a lot of lectures to general audiences all around, and I've just started talking about this kind of thing quite widely, and it has gone down very well.
My question is, suppose you are teaching back in a room full of ingressive thinkers.
Yes.
What tools do you use to, or ideas do you have about showing them the valuableness of congressive thinking? Mm-hmm. Do you think it's worthwhile to to just follow the aggressive way in that kind of space, or I guess how do you get buy-in for progressive
That's a
thinking in
great
that kind of
question, and it's
atmosphere?
something that I didn't talk about because of what I was trying to fit in the time. But I do believe that society has been rewarding ingressive behavior for a long time, whereas I think that a lot of times congressive behavior is much more beneficial to society. But if ingressive behavior is rewarded, then everyone will try to be as ingressive as possible to get those rewards, me included. Whereas if you create an environment where congressive behavior is rewarded, then I have seen people all veer towards being more congressive in order to be rewarded. So I begin every class with a very long introduction about ingressive and congressive behavior. And I stress how I will only value congressive behavior because I only want people who are collaborative and who want to understand things, and I will not take any showing off about how clever you are. And I say that I will accept any question. There are two types of question. There's the type of ingressive question, which is to show how clever you are. And there's the congressive type, which is where you're seeking to understand something more. And those are the types of questions that often start, this is a really stupid question, but. And I always say, those are not stupid questions. Anytime you're trying to understand something, it is valid. And anytime you contribute any thought, it is going to help us progress towards some understanding of something. So there is no notion of right and wrong. And I neutralize ingressive behavior by not letting people call out answers or put their hands up, but I pick their names randomly out of a pot, and then I ask them what they're thinking. And because I have set up the environment to be completely congressive, they're perfectly happy to say what they're thinking, or if they're not following, then they'll say they're not following, and then we can discover why they're not following, and then we've still learned something. And I have found this to be very valuable because amazingly, even in my art classes where white men are in the absolute minority, there's often only one or two of them in a class of 22, they still manage to dominate. If I don't somehow neutralize that, they will still be the ones calling out the answers. If I ask them the students to put their hands up, it will be the white men who put their hands up first. And eventually I will be able to persuade some other people, and the Asian girls will be the absolutely last people to put their hands up, despite the fact that I am one. And so somehow me standing at the front of being one doesn't help that. Whereas if I pick their names out, then everyone contributes something, and everyone feels absolutely fine contributing something, although they would never dare actually put their hand up. So that is one of the ways I have found to persuade the class to become more congressive. Thanks.
So correct me if I'm wrong, but I felt like a lot of your talk was kind of, the first part was about taking away, or like getting rid of words with strong connotations, or maybe trying to rid them of those connotations and replace them with other words or something. So but I also felt like ingressive was given a sort of negative connotation. I was wondering how you would reconcile that with that theme.
I'm only trying to get rid of gender connotations. I'm not trying to get rid of all connotations. And so yes, I'm betraying my own bias, which is that I truly believe that congressive behavior is more productive. If I said that I believe that feminine behavior is more productive, that would be exceedingly divisive, and I have enough men hating me on the internet already. I don't need any more. Whereas I think that if we can have a more sensible conversation. So just like we can talk about doing math outreach that's congressive rather than ingressive, whereas if you talk about math outreach to attract girls as opposed to boys, then it gets really stupid. And you get stuff like pink Barbie and pink Lego, and that doesn't make any sense. So I am open to, if people think that there is a benefit to being ingressive, I think there are some very specific situations in which I think ingressive behavior is important. For example, if you're doing emergency cardiac surgery, then you don't have time to take on board everyone's opinion. Or possibly if you're in the military, but then I'm not sure really what I think of the military. That's the most neutral way I can think of saying that. And I think that there are many situations where we filter for ingressive behavior where it's not necessarily productive, such as for positions of management, where to go up for promotion, you have to be quite ingressive, you have to sell yourself, you have to put yourself forward. Whereas when you're actually trying to get the best out of people, I'm not sure that ingressive behavior is at all helpful. In fact, I suspect it's obstructive. Another situation where we filter ingressively is elections. That's all I'm going to say about that.
For lunch. So please, both of you, ask your questions.
I was going to ask, you started by talking about your experience at the University of Cambridge, and I'm curious if you could talk about, because my belief at least is that the highest levels of mathematics as a field is still quite ingressive. But when you look around here, it's amazing to see all the people who obviously believe in the power of the congressive in mathematics. And I'm curious if you could kind of address your feelings about the highest level of our field and whether it is moving in the direction it needs to, or what maybe we could do to help in that as well.
Thank you. Do you want to say your questions well, and then I'll answer both?
Just in the interest of time, could you ask your question as well, and then we'll have one last response.
I wanted to thank you, first of all, because as an ingressive thinker, I would like to understand congressive thinkers better. That being said, it bothers me how poorly defined those morphisms of privilege are. I don't know if it's just because I don't understand them, and maybe at the Institute of the Art, it's a regular thing that everybody understands. Just so from the perspective of a more general audience, I don't quite understand if it's well defined at all. Thank you.
Thank you. So the well-definedness of those arrows at a strictly mathematical level is simply about subset inclusion. And that's all it is. So then we can ask ourselves what that subset inclusion is telling us in life. So the subset inclusion simply says every time you lose one element of your set, there's an arrow. And so that is a strictly mathematical structure. We can then ask, you're right, we can then ask what effect that has in society. And then it becomes a question of whether you believe that structural prejudice actually affects individuals, and that's a separate question. So if we can accept that there is structural prejudice, we can then move on to the question of whether it affects individuals. And if we separate out those questions, we can at least have a more sensible discussion about where the point of disagreement or agreement could be. And that's where part of it is mathematics, and then the other part becomes sociology. So I don't pretend to be a sociologist, but I say that if we start by extracting the mathematical structure, it gives us a basis for having the conversation. Thank you. And so the other question was, oh yes, so I really believe that the category theory community is very congressive, although there are certain aspects of it that are ingressive by accident, because all our interactions with university structures and publishing structures tend to veer towards the ingressive. However, I am very appreciative of the fact that the category theory community has been extremely collaborative online, for example, for a long time. There have been group blogs for a long time. There's a whole wiki project where everyone collaborates to explain parts of category theory. There are loads of people who just blog the whole time to explain their thought processes as they go along. I'm too scared to do that because I'm too congressive and I'm worried people will think I'm stupid. But there are people doing that the whole time. We've had a collaborative book written online, and I believe, I've always felt that that part of the research community at the absolute level of research is very congressive, whereas the sort of political parts I have found to be much more ingressive. So things like publishing and the sorts of referees reports that I've sometimes had complaining that I made my paper too accessible and that it seems to be stupid, or people who think that there are still people who think that if you give a talk that's intelligible, it means that you're not very intelligent and that your work isn't profound. So that still happens. And certainly in the context of a university environment, I found that the political structure in the university was extremely ingressive. And it was one of the reasons that I had to leave, because I didn't want to become like that. And I could feel myself becoming more ingressive to adapt to it. And I didn't want to. And so I left. I've since then been developing congressive ways to deal with ingressive environments, rather than becoming ingressive to match it. Just in the same way that I don't think that traditionally women have often been told that they should emulate traditional male behavior in order to be successful. You know, be confident and take risks and step outside your comfort zone and be resilient. I don't believe in any of those things. I hate taking risks. I don't ever leave my comfort zone, and I'm not resilient. But what I've done instead is I've expanded my comfort zone. And instead of taking risks, I create huge safety nets around me. So it looks like I'm taking a risk, but I'm not. And so I've been developing congressive ways to approach the ingressive world, because it still is an ingressive world, and if we just suddenly become congressive, then we might get shouted down. But I hope in the end we can sway things to be a bit more ingressive, and then maybe some of our problems of inclusivity will be improved. That's what I hope and believe anyway. And I hope that you'll help to achieve that great future world.